Right now, somewhere in this universe, a region of space smaller than a city holds more mass than 1 billion stars combined. Nothing escapes, not light, not time, not you. Over the next 2 hours, we will fall into the smallest black holes known to exist. We will witness the largest ever detected. We will watch stars get shredded. And we will explore ideas that could rewrite everything we understand about reality. If you enjoy this journey, consider liking and subscribing. Now, let us begin at the edge of the abyss. Imagine squeezing our entire planet into a space the size of a marble. Every mountain, every ocean, every person, crushed into something you could hold in your hand. The gravity coming off that tiny marble would be so intense that if you stood just a few feet away, you would never move again. You would be trapped forever. Now, imagine doing the same thing with a star 20 times more massive than ours. That is a black hole. But here is what most people get wrong. A black hole is not a hole. It is not empty space. It is the opposite. A black hole is the most dense thing in the known universe. So much matter packed into such a small space that the fabric of reality itself bends around it. Space-time curves so sharply that every possible path, even the path light takes, leads in only one direction, inward. This is confirmed science. We have images. We have measurements. We have detected the ripples black holes send through the universe when they collide. Think about light for a moment. Light is the fastest thing that exists. Nothing in the universe moves quicker. It travels at over 670 million miles per hour. At that speed, you could circle Earth more than 7 times in a single second. Light is so fast that we use it to define distance across the cosmos, and black holes stop it cold. Not because they grab light with some invisible hand, not because there is a wall. The reason is stranger. Near a black hole, space itself is falling inward faster than light can travel outward. Imagine trying to run up an escalator that moves faster than you can sprint. No matter how hard you try, you will never reach the top. You will be carried down. That is what happens to light near a black hole. Space is the escalator, and it is falling into the center faster than anything can escape. The boundary where this happens has a name. Scientists call it the event horizon. We will explore that boundary soon, but understand this first. The event horizon is not a surface you can touch. It is not made of anything physical. It is simply the point of no return. Cross it, and every direction you travel, forward, backward, left, right, even standing still, all paths lead to the center. What waits at the center is something our mathematics cannot fully describe. A point of infinite density, infinite curvature, a place where the known laws of physics break down completely. Scientists call it the singularity. But do not let the math fool you. Black holes are real objects. They exist in our galaxy. In fact, astronomers estimate there could be 100 million black holes in the Milky Way alone. Most of them are invisible. They drift through space, pulling on nothing, revealing themselves to no one. You could have one a few light years away, and unless it passed near a star or a cloud of gas, you would never know. Some black holes are small. If you can call something with the mass of several stars small, these formed from dying suns, and they populate galaxies like ours by the millions. Others are enormous beyond imagination. Sitting at the centers of galaxies, these monsters hold billions of stellar masses. They anchor entire spirals of stars in their gravitational grip. Without them, galaxies might not exist at all. And then there are the ones we have not yet found, black holes that may have formed in the first second after the universe began, primordial relics that could still be drifting through the darkness, waiting to be discovered. Over the next 2 hours, we will visit all of them. We will fall past the event horizon. We will watch stars get torn apart. We will hear the sound of 2 black holes colliding from over 1 billion light years away. But first, we need to understand the boundary itself. the invisible line that separates our universe from the unknown. What happens at the event horizon changes everything. Picture yourself floating in space, far from any star, drifting toward a black hole in the distance. At first, you see nothing unusual, just empty space. Maybe a faint warping of the stars behind it, their light bending around something you cannot directly observe. The black hole itself is invisible. There is no surface, no edge you can see, no warning sign. But there is a boundary, and once you cross it, the universe you knew is gone forever. The event horizon is not a physical barrier. You cannot touch it. You cannot feel it. If you were falling toward a large enough black hole, you might cross the event horizon without even realizing it happened. No alarm, no sensation, no flash of light. One moment you are in the universe. The next moment you are somewhere else entirely. Here is what makes this boundary so terrifying. From your perspective, falling inward, nothing seems wrong at first. Time feels normal. Space seems normal. You might look back and still see stars, still see light from the universe you left behind. But that light is the last you will ever receive from the outside. No signal you send will ever escape. No message, no call for help. You have crossed a one-way door that the universe has sealed shut. This is confirmed by general relativity. Einstein's equations predicted event horizons over a century ago, and in 2019, scientists captured the first direct image of one, a glowing ring of superheated gas surrounding a shadow. That shadow was the event horizon of a supermassive black hole at the center of galaxy Messier 87, over 55 million light-years away. But what happens on the other side? What would you experience if you actually fell through? The answer depends on the size of the black hole, and this is where things get strange. For smaller black holes, the ones formed from collapsing stars, the event horizon sits close to the center. The gravitational pull changes rapidly over short distances. Your feet, being closer to the center than your head, would feel a much stronger pull. This difference in gravity would stretch you violently. Scientists have a word for this process, and we will explore it in the next chapter. But understand this much now. For a small black hole, you would be torn apart before you ever crossed the event horizon. For supermassive black holes, the situation is different. These monsters are so large that the event horizon sits far from the center. The change in gravity across your body would be gentle, almost unnoticeable. You could fall through the event horizon of the black hole at the center of our galaxy and feel nothing unusual for hours, maybe longer, but do not mistake gentle for safe. You are still falling toward the center, and nothing, not the most powerful rocket ever built, not light itself, can reverse your course. The destination is inevitable. Only the journey varies. There is another effect worth considering. From the perspective of someone watching you fall from a safe distance, something bizarre happens. They would see you slow down as you approach the event horizon. Your image would stretch and redden. Time itself, as they observe it, would seem to crawl for you. They would watch you approach the boundary forever, never quite crossing it. Your frozen image fading into darkness over billions of years. Meanwhile, from your perspective, you fell through in an instant. This is not science fiction. This is what Einstein's equations demand. Time moves differently depending on how deep you are in a gravitational field. Near a black hole, that difference becomes extreme. And yet the event horizon is just the beginning. Beyond it lies something even more disturbing. A place where the gentle fall becomes a violent death. Your body is about to be stretched into something unrecognizable. Let us put you in a spacesuit and drop you toward a black hole. Not a simulation, not a thought experiment. The real thing. What would the final moments of your existence actually feel like? The first thing you notice is the view. As you fall closer, the black hole does not look like a dark circle. It looks like a lens. Light from stars behind it bends around the edges, creating a bright ring. Stars that should be hidden behind the black hole appear displaced, smeared, sometimes duplicated. The entire sky warps into unfamiliar shapes. Constellations you have known your whole life twist into something alien. This is gravitational lensing, confirmed by observation. Einstein predicted it, and astronomers have photographed it around black holes and galaxies throughout the universe. As you continue falling, the distortion grows. The ring of bent light around the black hole becomes sharper, brighter. The darkness at the center expands in your vision. You are accelerating now, pulled by a gravity stronger than anything you have ever experienced. But here is something strange. You do not feel the acceleration. Gravity does not push you. It pulls everything around you equally. Your body, your suit, the air in your lungs, all of it falls together. You feel weightless, peaceful almost, like floating in calm water. This feeling will not last. The danger is not the fall. The danger is the difference in how hard gravity pulls on different parts of your body. Your feet are closer to the black hole than your head. Even if that difference is only a few feet, near a small black hole, the gravitational pull on your feet can be dramatically stronger. This creates a stretching force. At first, the stretch is minor, a slight tension, like being gently pulled in two directions. But as you fall deeper, the difference in gravity increases. The pull on your feet intensifies, while your head experiences slightly less. The tension builds. Your spine elongates. Your body begins to distort. This is where size matters. If you are falling into a stellar mass black hole, one formed from a collapsed star with maybe 10 or 20 times the mass of our own star, the stretching becomes lethal long before you reach the event horizon. The difference in gravity across your body grows so extreme that your tissues cannot hold together. You are pulled apart, not quickly, not cleanly. Atom by atom, your body elongates into a thin stream of matter spiraling toward the center. Scientists call this spaghettification. The term sounds almost playful. The reality is anything but. But suppose you chose a different target. The supermassive black hole at the center of our galaxy has over 4 million stellar masses. Its event horizon sits about 7 million miles from the center. At that distance, the change in gravity across a human body is tiny, less than 1% of 1%. You could cross the event horizon and feel almost nothing for a while. The problem is that once you cross, you cannot stop falling. And as you continue inward, the gravitational gradient steepens. What felt gentle at the horizon becomes violent as you approach the center. The stretching begins. The same fate awaits. You simply have more time to contemplate it. There is another factor most people forget. As you fall, time behaves strangely. From your perspective, the fall feels normal. Seconds pass like seconds. But if you could somehow look back at the universe outside, you would see it aging rapidly. Stars moving faster, galaxies evolving, the universe racing toward its distant future while you drift toward your end. You cannot send a message back. You cannot warn anyone. Everything you see from inside is the last light that will ever reach you from the outside universe. And soon, even that fades. Ahead of you, there is only darkness. And at the center of that darkness waits something our physics cannot explain. But before we reach the singularity, we need to understand what happens to your body in those final moments. The stretching is about to become extreme. The word sounds ridiculous, spaghettification, like something from a cartoon, but what it describes is one of the most violent processes in the universe, and it happens to everything that falls into a black hole. Every star, every planet, every astronaut who drifts too close. Here is how it works. Gravity weakens with distance. Stand on Earth, and the ground pulls you down with a certain force. Climb a tall mountain, and that force decreases slightly. Not enough to notice, but it is measurable. Now imagine gravity so powerful that the difference between your head and your feet matters. Not a slight difference. A difference that could tear you apart. Near a black hole, that gradient becomes extreme. If your feet are 1 meter closer to the center than your head, they might experience hundreds or thousands of times more gravitational pull. Your feet accelerate faster than your head. Your body stretches. At the same time, gravity pulls from all sides toward a single point. This creates a squeezing effect perpendicular to the stretch. While you are being elongated vertically, you are being compressed horizontally. Your body becomes thinner and thinner while growing longer and longer. The result is a strand, a ribbon of matter that once was you, now stretched across thousands of miles, spiraling toward the center of the black hole. This is confirmed physics. In 2020, astronomers observed a star being spaghettified in real time. The star wandered too close to a supermassive black hole, about 250 million light-years from Earth. Telescopes detected a sudden flash of light as the star was torn apart. Over the following months, they watched the debris spiral into the black hole, creating a temporary glow visible across half the observable universe. They called this a tidal disruption event. The tidal forces, the same kind of forces that cause ocean tides on Earth from our moon's gravity, were strong enough to shred a star. If a star cannot survive, what chance does a human have? Let us return to the numbers. For a stellar mass black hole, roughly 10 times the mass of our star, the tidal forces become lethal at about 200 miles from the event horizon. You would be stretched into a stream of atoms before you ever cross the point of no return. Death would come quickly, at least. For the supermassive black hole at our galaxy's center, the numbers change. The event horizon is so far from the center that the tidal forces there are weak. You could survive the crossing, but survival only delays the inevitable. As you continue falling inward, the gradient steepens. Within hours, maybe less, the stretching begins. And once it starts, there is no stopping it. But here is something even stranger. From your perspective, the experience might not feel like being pulled apart, at least not at first. Remember, you are in free fall. Everything around you falls at the same rate. Your body does not feel the pull of gravity directly. What you feel is the difference in pull across your body. At first, that difference feels like mild tension, a stretch, uncomfortable, but not immediately painful. Then it intensifies. Your joints ache, your spine cracks, your skin tears. The tension becomes unbearable, and still you fall. In the final moments, you are no longer recognizably human. Your atoms stream toward the center in a thin filament, joining the mass of the black hole. Everything you were becomes part of the singularity. But what exactly is the singularity? What happens at the very center where all that matter collects? This is where our understanding ends. The equations break down, the physics fails. We are left with a mystery that challenges everything we think we know about reality. And the answer might rewrite the laws of the universe. Every path inside a black hole leads to the same destination, the singularity, a point at the center where matter has been crushed beyond any limit we can calculate. Density becomes infinite. Curvature becomes infinite. The equations we use to describe the universe produce answers that make no sense. And that is the problem. When physicists say the singularity has infinite density, they are not describing something real. They are admitting that our mathematics has failed. The equations of general relativity, Einstein's masterpiece that describes gravity as the curvature of space-time, work beautifully everywhere else in the universe. They predict the bending of light, the expansion of space, the behavior of orbiting planets. But at the singularity, they collapse. This tells us something important. Our understanding of physics is incomplete. Somewhere in the extreme conditions at the center of a black hole, the rules change, and we do not yet know the new rules. Here is what we think happens, based on our best current theories. As matter falls inward, it gets compressed. The density increases. At some point, The density exceeds anything found in ordinary matter. Even neutron stars, where atoms are crushed so tightly that protons and electrons merge into neutrons, cannot compare. The matter inside a black hole reaches a state beyond neutrons, beyond quarks, beyond anything we have names for. Eventually, all that matter concentrates into a region smaller than an atom, perhaps smaller than a single particle. All paths through space-time curve so sharply that they converge on this point. Time itself, according to the equations, comes to an end, not in the sense that a clock stops ticking, but in the sense that there is no future beyond the singularity. It is a boundary, not just in space, but in time. This is theoretical. No one has observed a singularity directly. By definition, we cannot. The event horizon prevents any information from escaping. Everything we know about the singularity comes from mathematics and educated guesses. But most physicists believe that the singularity, as described by general relativity, is not real. It is a sign that a new theory is needed. When you get answers like infinity, it usually means your equations are missing something. The missing piece is probably quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the smallest scales, particles and waves, probabilities and uncertainties. At the singularity, where everything is compressed into an unimaginably small space, quantum effects must become important. But here is the frustrating part. We do not yet have a theory that combines quantum mechanics and gravity in a consistent way. The two pillars of modern physics refuse to work together at the singularity. This is one of the greatest unsolved problems in science. A theory of quantum gravity would explain what really happens at the center of a black hole. It might reveal that the singularity is not a point of infinite density, but something else entirely. Perhaps a tunnel to another region of space-time, perhaps a new universe being born, perhaps something we cannot yet imagine. Some researchers speculate that the singularity is where our universe ends and something new begins. Others think information that falls in might be preserved in ways we do not understand, encoded on the event horizon like words on a page. We do not know, and until we do, the singularity remains the ultimate mystery, a place where the universe hides its deepest secrets behind a veil we cannot lift. But black holes are not just destinations for falling matter, they are also born in some of the most violent events the cosmos has ever seen. The death of a massive star is about to create something eternal. Every black hole begins with destruction, the kind of destruction that outshines entire galaxies for a few brief weeks, the kind that scatters elements across light years of space, the kind that turns a star into something eternal. This is the story of how stellar black holes are born. Start with a massive star, not like ours. Ours is relatively small and will die quietly in a few billion years, swelling into a red giant before shedding its outer layers and fading into a white dwarf. No black hole, no explosion, just a slow, gentle death. But stars more than 20 times the mass of ours live very different lives. They burn hotter, they burn faster, and when their fuel runs out, they do not fade, they explode. For millions of years, the star fuses hydrogen into helium in its core. The energy from this fusion creates outward pressure that balances the inward pull of gravity. The star stays stable, bright, massive, dominant. But fusion produces heavier elements over time. Helium fuses into carbon, carbon into oxygen, oxygen into silicon. Each stage burns faster than the last. The final stage, fusing silicon into iron, lasts only about a day. And then everything stops. Iron cannot fuse to produce energy. It absorbs energy instead. The moment the core fills with iron, the outward pressure vanishes. Gravity wins instantly. What happens next takes less than a second. The core collapses at nearly a quarter of the speed of light. Layers of the star that took millions of years to build come crashing inward. The density skyrockets. Temperatures reach billions of degrees. And then the collapse suddenly halts as the matter reaches nuclear density, the point where particles resist being pushed any closer together. The infalling material rebounds off this dense core like a ball bouncing off a wall. A shock wave races outward through the star. This is the supernova. The explosion is beyond imagination. For a few weeks, a single dying star releases more energy than our star will produce in its entire 10 billion year lifetime. The outer layers blast into space at tens of thousands of miles per second, carrying heavy elements forged in the final moments of the star's life. These elements, iron, gold, uranium, seed the universe with the building blocks of planets and people. But the core remains. If the original star was massive enough, that core cannot support itself even at nuclear density. Gravity overwhelms everything. The core continues collapsing, shrinking past the point of no return until it forms a black hole, a region of space where matter has compressed so densely that escape becomes impossible. This is confirmed by observation. We have detected dozens of stellar black holes in our galaxy through their gravitational effects on companion stars. When a black hole orbits close to a normal star, it pulls matter from its partner. That matter spirals inward, heats up, and emits X-rays we can see from Earth. The masses of these stellar black holes range from about 5 to several tens of times the mass of our star. They are small compared to the giants at the centers of galaxies, but they are everywhere. Astronomers estimate 100 million of them wander through the Milky Way. Most are invisible, pulling on nothing, revealing themselves to no one. You could be a few light years from one right now and never know. But not all stellar black holes form the same way. Some are born from mergers, some might form from direct collapse without an explosion, and some have masses that should not exist according to our current understanding. The smallest black hole ever found pushes the limits of what we thought possible. The final day of a massive star's life moves faster than anything else in its history. After millions of years of steady burning, the end comes in hours, and the actual collapse? Less than a second. Let us slow it down. The star has spent its life fighting gravity. Nuclear fusion in the core creates energy, and that energy pushes outward, balancing the tremendous weight of the outer layers. This balance has held for millions of years, but fusion is not forever. The fuel runs out in stages, each stage shorter than the last. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands. Carbon burning lasts centuries. Oxygen burning lasts months. Silicon burning, the final stage, lasts about a single day. When silicon fuses, it produces iron, and iron is the end of the road. Fusing iron does not release energy, it consumes it. The moment iron fills the core, the star's engine dies. What follows is catastrophic. Without fusion to create outward pressure, gravity has nothing to oppose it. The core begins to collapse, not slowly, not gently, at nearly 70,000 miles per second. In less than 1 second, a core roughly the size of Earth compresses into a ball about 12 miles across. Try to picture that, a region larger than our planet, containing more mass than our star, crushing down into something smaller than a city. The compression is so violent that electrons are forced into protons, creating neutrons. For a brief moment, the core becomes a neutron star, an object so dense that a single teaspoon weighs billions of tons. But if the original star was massive enough, even neutron pressure cannot hold. Gravity does not stop. It overwhelms the nuclear forces that keep particles apart. The collapse continues, accelerating past every barrier physics can offer. At some point, the collapsing matter crosses its own event horizon. A black hole is born. Meanwhile, the outer layers of the star are still falling inward, unaware that the core has already transformed into something inescapable. They crash into the forming black hole or rebound off the brief neutron star phase, creating a shockwave of unimaginable power. This shockwave tears through the star. It heats the outer layers to temperatures where new nuclear reactions occur. Heavy elements form in the explosion itself. Gold, platinum, uranium, forged in seconds. The shockwave reaches the surface and the star explodes outward. This is the supernova. From Earth, it appears as a new star in the sky, sometimes visible in daylight. Ancient astronomers recorded these events without understanding what caused them. But the core is gone. Where there was once a furnace of nuclear fire, there is now only silence. A black hole sits in the debris, invisible except for its gravity. Matter that falls too close spirals in. Energy radiates from the infalling material, but the black hole itself reveals nothing. This entire sequence, from core collapse to supernova to black hole formation, happens in seconds. The star spent millions of years building its layers. Gravity destroyed them almost instantly. And yet not every stellar death produces a black hole. Some leave behind neutron stars instead. The difference depends on mass, and that difference creates a mystery. There is a gap in the masses where black holes seem not to exist. Scientists are still arguing about why. But before we explore that gap, let us examine the other extreme. The smallest black hole ever confirmed challenges everything we thought we knew about how compact these objects can be. When scientists announced the discovery in 2020, it sparked immediate debate. A black hole with only 3.3 times the mass of our star, barely larger than the heaviest neutron stars, sitting right at the edge of what should be possible. They called the system 2-mass J05215658 plus 4359220. The name is forgettable. The discovery is not. For decades, astronomers believed there was a clear boundary between neutron stars and black holes. Neutron stars, the crushed cores of dead stars, could reach about 2 to 2.5 stellar masses before collapsing further. Black holes, on the other hand, seem to start around 5 stellar masses. The zone in between was strangely empty. This new discovery landed right in that gap. The black hole orbits a red giant star about 1,500 light-years from Earth. By studying how the red giant wobbles, astronomers calculated the mass of its invisible companion, 3.3 stellar masses, and the companion was too compact and too dark to be anything other than a black hole. At that mass, the black hole would be tiny. Its event horizon would measure only about 12 miles across, small enough to fit inside a medium-sized city. Yet within that space lies more mass than 3 of our stars combined. This challenges some theories about how black holes form. The traditional story says massive stars explode in supernovae and leave behind black holes with masses starting around 5 times that of our star. Below that, you get neutron stars instead. The gap between 2 and 5 stellar masses seemed like a rule of nature. But this discovery suggests the gap may not be as empty as we thought. Either some black holes form through unusual processes that produce lower masses, or our understanding of stellar explosions needs revision. One possibility is that some stars collapse quietly. Instead of exploding in a brilliant supernova, they might implode directly into black holes without much fanfare. This could produce black holes at the lower end of the mass range. Another possibility involves binary systems. If 2 neutron stars orbit each other and eventually merge, the combined mass could exceed the limit and collapse into a small black hole. Gravitational wave detectors have already observed such mergers. The remnants would be lightweight black holes, just above the neutron star limit. What makes this discovery even more striking is how close the object is. 1,500 light-years sounds like a vast distance, but in galactic terms, it is practically next door. If small black holes like this one are common, there could be many more lurking nearby, invisible against the background of space. Finding them is difficult. Small black holes do not emit light. They do not glow unless matter falls into them. If one drifts through empty space, pulling on nothing, we would never detect it. Only when a black hole has a companion, a star it can gravitationally influence, do we have a chance to measure its effects. Astronomers estimate that for every black hole we have found, thousands more remain hidden. The Milky Way could be teeming with these small, silent remnants. They drift among the stars, carrying the mass of collapsed suns, revealing themselves only through subtle gravitational tugs. But small black holes are only part of the story. Some black holes live in pairs, locked in a gravitational dance that will one day end in catastrophe. Two predators circling each other, neither willing to let go. In the darkness between stars, two black holes spiral toward each other. They have been dancing for millions of years, maybe billions. Each orbit brings them slightly closer. Each pass drains a little more energy from their motion, and one day the dance will end. When it does, the collision will shake the fabric of space-time itself. Binary black hole systems form in several ways. Sometimes two massive stars are born together, orbiting each other from the beginning. When both stars die and collapse, they leave behind two black holes still locked in mutual orbit. The same gravitational bond that held the stars together now holds their corpses. Other times, black holes find each other later, in dense environments like globular clusters, where hundreds of thousands of stars crowd into a region only a few dozen light-years across. Black holes can sink toward the center and capture each other through close encounters. These pairings are chaotic, formed by chance rather than shared birth. However they come together, the result is the same: two of the most extreme objects in the universe, bound by gravity, falling toward a common fate. Here is what makes binary black holes special. As they orbit, they lose energy by emitting gravitational waves. These are ripples in space-time itself, spreading outward at the speed of light. We cannot see them with telescopes, but we can detect them with instruments that measure the stretching and squeezing of space as the waves pass. The energy carried by gravitational waves comes from the orbit itself. As energy leaves, the black holes spiral closer. The process is incredibly slow at first. Two black holes separated by millions of miles might take billions of years to merge, but the closer they get, the faster they lose energy. The final spiral accelerates rapidly. In the last seconds before collision, the black holes whip around each other at a significant fraction of the speed of light. They complete dozens of orbits per second. The gravitational waves intensify, rising in frequency and amplitude. Scientists call this the chirp, because if you converted the waves to sound, it would resemble a rising tone that ends abruptly. Then impact. The two event horizons merge. The combined black hole shudders and distorts, briefly assuming a lumpy, unstable shape. Within milliseconds, it settles into a smooth, spinning configuration. The ring-down phase sends out final gravitational waves as the new black hole achieves equilibrium. The energy released is staggering. When two black holes of 30 stellar masses each collide, roughly 3 stellar masses of material converts entirely into gravitational wave energy. In that fraction of a second, the merger radiates more power than all the stars in the observable universe combined, not as light, as gravity. We detected this for the first time in 2015. Two black holes, about 36 and 29 stellar masses respectively, merged roughly 1.3 billion light-years away. The gravitational waves traveled across the cosmos, weakening as they spread, until they reached Earth as a faint vibration that stretched and compressed our planet by less than the width of a proton. We heard it anyway. Since then, scientists have detected hundreds of binary black hole mergers. Each one teaches us something new about how these systems form, how black holes spin, and how gravity behaves under extreme conditions. But there is still a mystery. The masses we detect sometimes fall into ranges that our theories cannot explain. Something unexpected is happening with the middle weights. When astronomers started counting black holes, they expected to find them at all sizes. Small ones, from modest stellar deaths, large ones from massive stellar deaths, a smooth distribution from a few stellar masses up to dozens. Instead, they found gaps, The lower mass gap sits between roughly 2 and 5 stellar masses. Neutron stars top out around 2.5 stellar masses. Black holes seem to start around 5. For years, the zone between appeared empty. We discussed one recent exception, but it remains unusual. Most stellar black holes cluster above 5 masses. The upper mass gap is even stranger. It stretches from roughly 50 to 130 stellar masses. Theory says black holes should not form in this range from normal stellar evolution. The reason has to do with how massive stars die. Remember that when a star's core becomes iron, it collapses. But for extremely massive stars, something different happens first. Before iron forms, the core reaches temperatures where photons convert into pairs of electrons and their antimatter counterparts, positrons. This pair production removes pressure support from the core, triggering an early collapse. The collapse releases energy that ignites explosive oxygen and silicon burning. Instead of forming a black hole, the entire star blows apart. Nothing remains. No neutron star, no black hole, just an expanding cloud of debris. This is called a pair instability supernova. It happens for stars that would have produced black holes between roughly 50 and 130 stellar masses. The star destroys itself so completely that nothing survives. Above 130 masses, the explosion cannot unbind the star. Gravity wins. A black hole forms directly, skipping the gap. Below 50 masses, normal supernovae produce black holes without triggering pair instability. So, theory predicts a gap. And for years, observations agreed. The black holes we found clustered below 50 masses, with a few exceptional giants above 130. Then gravitational wave detectors started finding anomalies. In 2019, a merger was detected involving a black hole of about 85 stellar masses, right in the forbidden zone. The discovery forced theorists to reconsider. Maybe some black holes in the gap form through mergers of smaller black holes. If two 30-mass black holes combine, the result would sit in the previously forbidden range. Hierarchical mergers, where the products of earlier mergers combine again, could populate the gap over time. Another possibility involves unusual stars. Some stars in the early universe, containing fewer heavy elements than modern stars, might have behaved differently. They could have lost less mass to stellar winds, retained more material, and collapsed into black holes within the gap. Or perhaps our models of pair instability are incomplete. The boundaries of the gap depend on nuclear physics at extreme temperatures. Small changes in those calculations could shift the edges. What we know is that the gap exists for most black holes, but is not absolute. Some objects cross the boundaries, and those exceptions might tell us more about black hole formation than all the normal cases combined. But stellar mass black holes, even the mysterious ones, are tiny compared to what lurks between the extremes. There is an entire class of black holes we struggle to find, massive enough to dwarf stellar remnants, small enough to hide from our surveys. The missing middle children of the black hole family, between the stellar black holes formed from dying stars and the supermassive giants anchoring galaxies, lies a vast unknown. Black holes with masses from 100 to 100,000 times that of our star. They should exist. Physics permits them. Logic suggests them. We just cannot find many of them. Intermediate mass black holes are the most mysterious members of the black hole family. They are too large to form from single stellar collapses. They are too small to be the ancient monsters at galactic centers. They occupy a middle ground that remains frustratingly dark. Why do we expect them to exist? The argument goes like this. Supermassive black holes did not appear fully formed. They had to grow from something smaller, seeds. Those seeds could have been intermediate mass black holes that merged and fed their way to enormity over billions of years. Without the middle step, we struggle to explain how the giants got so big so fast. But finding intermediate mass black holes is hard. They do not form from ordinary stellar deaths, so they are not scattered everywhere like stellar remnants. They are not massive enough to dominate galactic cores like supermassive black holes. They hide. One way to form them involves dense stellar environments. Picture a globular cluster, a spherical swarm of hundreds of thousands of stars packed into a region, maybe 100 light-years across. At the center, stars crowd together. Collisions happen. Massive stars merge into hypermassive stars that collapse directly into black holes larger than any single star could produce. Once formed, an intermediate mass black hole at the center of a cluster would sink deeper due to dynamical friction, interacting gravitationally with surrounding stars. It would continue to grow, swallowing stars and smaller black holes that wander too close. Over billions of years, it could reach thousands of stellar masses. Another formation path involves runaway mergers of stellar black holes. If black holes in a dense cluster collide repeatedly, the products grow generation after generation. Eventually, the merged remnant enters intermediate mass territory. There is also the possibility that some intermediate mass black holes are primordial, formed in the early universe through mechanisms unrelated to stellar evolution. We will explore that idea later. So where are the candidates? The strongest evidence comes from a source called HLX-1, located in a galaxy about 290 million light-years away. This object emits X-rays consistent with a black hole actively consuming matter. By analyzing how the brightness changes and estimating the temperature of the infalling material, researchers calculated a mass around 20,000 stellar masses. Not supermassive, not stellar, intermediate. Another candidate appeared in gravitational wave data from 2019. The merger produced a black hole of roughly 142 stellar masses, still below the traditional intermediate threshold of 100 stellar masses, but right at the edge. Some consider it the first confirmed intermediate mass black hole formed from a collision we witnessed. Others remain skeptical. Measuring the masses of distant objects involves significant uncertainty. Some candidates might be misidentified. Some might have explanations that do not involve black holes at all. What we can say is that the intermediate mass range is not empty. Candidates exist, but compared to the millions of stellar black holes in our galaxy and the supermassive ones in every large galaxy, intermediate mass black holes remain rare, or at least rarely detected. The search continues. New telescopes, new gravitational wave detectors, new techniques for finding invisible objects through their gravitational effects. Somewhere in the darkness, the missing link waits to be found. Scattered around our galaxy are roughly 150 ancient star cities, globular clusters. Spherical collections of hundreds of thousands of stars, bound together by gravity, orbiting the Milky Way like satellites. They are among the oldest structures in the universe, formed billions of years ago when the cosmos was young, and they might be hiding exactly what we are looking for. Globular clusters are strange places. The stars inside them pack together at densities unimaginable in our neighborhood. Near the center of a dense cluster, stars might be separated by only a fraction of a light-year. In our region of the galaxy, the nearest star is over 4 light-years away. Cluster cores are crowded by comparison. This crowding changes everything. Stars interact. They pass close to each other, exchanging energy, altering orbits. Sometimes they collide outright, merging into more massive objects. In such environments, unusual things can form. Here is why clusters matter for intermediate mass black holes. When massive stars die, they leave behind stellar black holes. In a normal galaxy, these black holes drift apart, rarely encountering each other. But in a cluster core, black holes sink toward the center through a process called mass segregation. Heavy objects lose energy to lighter stars and fall inward. Given enough time, black holes accumulate in the densest region. Once clustered together, black holes can interact. They form binaries. They merge. Each merger produces a slightly larger black hole. If this happens repeatedly over billions of years, the product could grow into the intermediate mass range. Computer simulations support this scenario. They show that dense clusters can produce black holes of hundreds or even thousands of stellar masses through sequential mergers. The most massive black hole dominates the core, continuing to grow by swallowing smaller black holes and occasionally entire stars that wander too close. Direct evidence is harder to obtain. We cannot see intermediate mass black holes directly. We can only infer their presence through their effects on surrounding stars. One approach measures the velocities of stars near the cluster center. If an intermediate mass black hole lurks there, its gravity would accelerate nearby stars to higher speeds than expected from the visible mass alone. Astronomers have tried this technique on several clusters with mixed results. Some show hints of excess mass, others do not. Another approach looks for X-ray emissions. If an intermediate mass black hole captures gas from passing stars, that gas heats up as it spirals inward, emitting X-rays. Several globular clusters associated with our galaxy and nearby galaxies have X-ray sources that could be intermediate mass black holes feeding at low rates. The emissions are faint, making definitive identification difficult. Then there is the gravitational wave approach. When intermediate mass black holes merge with stellar black holes, they produce gravitational waves in a frequency range that current detectors can observe. The more mergers we detect, the better we can estimate how common intermediate mass black holes are in clusters. So far, the picture is incomplete. Some clusters probably host intermediate mass black holes. Others might not. The formation efficiency depends on cluster density, age, and history. Not every cluster produces a monster. But the search has intensified. Every gravitational wave detection, every X-ray survey, every careful measurement of stellar velocities brings us closer to understanding where intermediate mass black holes live. And understanding where they live helps explain how the largest black holes in the universe came to be. One black hole forms from a collapsing star, another forms nearby. Gravity pulls them together over millions of years. They merge. The product is larger than either parent. Now repeat. The merged black hole encounters another. They combine. The product grows, again and again, generation after generation, starting with black holes of 10 or 20 stellar masses, ending with something far more massive. This is the runaway merger theory, a way to build intermediate mass black holes without needing any single extraordinary event. The logic is elegant. Dense environments produce stellar black holes regularly. Those black holes sink toward the densest regions. They encounter each other. They merge. Each merger releases gravitational waves, which carry energy away, allowing the remaining black hole to settle into a tighter orbit with the next potential partner. In simulations, this process can produce black holes of hundreds or even thousands of stellar masses within a few billion years. Not quickly enough to explain the supermassive black holes seen in the early universe, but fast enough to create a population of intermediate mass objects in old globular clusters and dense galactic nuclei. There is observational support for this idea. Gravitational wave detectors have caught mergers that seem to involve black holes already too large to have formed from single-star collapses. These are probably second or third generation black holes, products of earlier mergers that have merged again. One event from 2019 involved a black hole of approximately 85 stellar masses, which should not exist if formed directly from a star. The most likely explanation is that this object was itself a merger remnant, a black hole formed when two smaller black holes combined sometime in the past. But runaway mergers face challenges. First, each merger imparts a gravitational kick to the resulting black hole. When two black holes combine, the gravitational waves they emit are not perfectly symmetric. This asymmetry pushes the merged black hole in one direction, sometimes at speeds of hundreds of miles per second. If the kick is strong enough, the black hole can be ejected from its home cluster entirely, ending the chain of mergers. Second, merger products spin rapidly. The angular momentum of the incoming black holes transfers to the final product. Highly spinning black holes might merge differently than slowly spinning ones, affecting the rate at which chains can continue. Third, the environment matters. Only the densest clusters provide enough encounters for runaway merging to work. Most stellar black holes in the galaxy drift alone, never encountering a partner. Only the lucky few in crowded regions have a chance to participate. Despite these challenges, the theory remains the leading explanation for how intermediate mass black holes form in the present universe. Not from single catastrophic events, but from slow accumulation, small steps toward enormity. And once an intermediate mass black hole forms, it can continue growing by consuming stars, gas, and smaller black holes. The chain does not have to stop. Given enough time and fuel, an intermediate mass black hole could grow into something even larger. But we have already found one candidate that might show this process in action. Roughly 290 million light-years from Earth, in a galaxy catalogued as ESO 243-49, an X-ray source flickers. It flares and dims over weeks and months. It sits not at the galaxy's center, but off to the side, embedded in what might be the remnant of a smaller galaxy being consumed. Scientists call it HLX1, Hyperluminous X-ray Source 1, and it might be the best evidence we have for an intermediate mass black hole. What makes this object special is its brightness and behavior. Ordinary stellar mass, black holes eating gas from companion stars produce X-rays, but they have limits. A black hole can only consume material so fast before radiation pressure pushes incoming gas away. This limit, called the Eddington limit, depends on mass. The more massive the black hole, the higher the limit. HLX1 is too bright to be a stellar mass black hole, eating at its maximum rate. The X-ray luminosity requires either a black hole far more massive than any stellar remnant, or a stellar black hole somehow violating the rules. When researchers modeled the emission, they concluded that HLX1 hosts a black hole of approximately 20,000 stellar masses. That places it firmly in intermediate mass territory. Not as large as the millions or billions of stellar masses found in galaxy centers. Not as small as the black holes formed from individual dying stars. But there is more. HLX1 sits in what appears to be a small star cluster. This cluster might be the stripped core of a dwarf galaxy that fell into the larger host. If a smaller galaxy contained an intermediate mass black hole at its center, and that galaxy was swallowed by a larger one, the black hole would be left behind as the dwarf was torn apart. This scenario makes sense. Many galaxies grow by consuming smaller neighbors. The smaller galaxies might carry their own black holes, intermediate in mass because their hosts were too small to grow supermassive ones. These imported black holes would wander the outskirts of their new home, occasionally revealing themselves through X-ray outbursts when gas falls in. HLX1 showed exactly this kind of variable emission. For years, it flared brightly, then faded, then flared again. The pattern suggested a companion object, maybe a star, orbiting the black hole and periodically feeding it material. Recent observations have shown the outbursts becoming weaker and less frequent. The companion may have been largely consumed. Eventually, HLX1 might go quiet, its black hole becoming invisible once more. This is the frustrating reality of hunting intermediate mass black holes. We can only see them when they are feeding. When the fuel runs out, they vanish into darkness. How many quiet intermediate mass black holes drift through galaxies, too far from any star to consume, invisible to all our instruments? We do not know, but HLX1 proves they exist. At least one intermediate mass black hole is out there, caught in the act of eating. Where there is one, there must be others. The question now is how many, and whether they can help explain the origins of the true monsters, the black holes that anchor entire galaxies. At the center of nearly every large galaxy sits something that should be impossible. A black hole so massive that it contains not thousands, not millions, but sometimes billions of times the mass of our star. compressed into a region smaller than our planetary system, dominating the gravitational landscape for thousands of light years in every direction. These are the supermassive black holes, the anchors of galaxies, the engines of the brightest objects in the universe, and we still do not fully understand how they exist. The smallest supermassive black holes weigh in at around 100,000 to 1,000,000 stellar masses. These sit at the centers of dwarf galaxies and small spirals. The largest exceed 10 billion stellar masses. These monsters dominate giant elliptical galaxies, warping space so severely that time itself flows differently near their influence. Our own galaxy, the Milky Way, hosts a relatively modest, supermassive black hole called Sagittarius A star. It has about 4 million stellar masses, modest by supermassive standards, but still enormous compared to anything else we encounter in daily astronomy. The discovery of supermassive black holes came gradually over decades. In the 1960s, astronomers found quasars, objects that looked like stars, but shone with the brightness of entire galaxies from billions of light years away. Nothing known could produce that much energy from such a small region. The only explanation that worked involved matter falling into an incredibly massive black hole. Later observations confirmed that most large galaxies harbor central black holes. Even quiet galaxies like ours, which lack a brilliant quasar, still contain dormant giants. They are not feeding much right now, so they do not shine, but the mass is there, detectable through its influence on nearby stars. Measuring that influence requires patience. Stars near the galactic center orbit the black hole, and by tracking their paths over years, astronomers can calculate the mass they must be circling. For the Milky Way, this technique has produced extraordinary data. Stars swing around Sagittarius A star at thousands of miles per second, completing orbits in as little as 16 years. The speed and path reveal the central mass. This work won the Nobel Prize in Physics in 2020. Direct proof of a supermassive black hole through stellar orbits. But knowing supermassive black holes exist does not explain how they formed. The universe is only about 13.8 billion years old. That sounds like a long time, but building a billion stellar mass black hole from scratch takes enormous amounts of eating. If a black hole consumed matter at the maximum possible rate since the universe began, it would still struggle to reach the masses we observe. Even stranger, we find supermassive black holes in the very early universe. Quasars, shining when the cosmos was less than 1 billion years old. Their black holes were already enormous. How did they grow so fast? This is one of the biggest open questions in astrophysics. Several theories compete. Some propose that the first black holes were born massive, collapsing directly from enormous gas clouds without forming stars first. Others suggest rapid mergers of intermediate mass black holes. Still others invoke exotic physics in the early universe. We will explore these ideas soon, but first, understand the scale. Supermassive black holes are not just large, they are the dominant gravitational actors in their regions of space, and their influence shapes the galaxies around them. Building a supermassive black hole is a problem of time and supply. You need an enormous amount of mass to fall into a single location, and you need it to happen faster than conventional physics seems to allow. Let us explore the leading theories. The first possibility is that supermassive black holes grew from stellar seeds. Imagine the early universe, filled with massive stars that lived fast and died young. These first stars, made of pure hydrogen and helium, could have been hundreds of times the mass of our star. When they collapsed, they left behind black holes of perhaps 100 to 1,000 stellar masses. If those seeds then fed continuously, consuming nearby gas at high rates, they could grow over billions of years into supermassive black holes. The problem is the rate. There is a maximum speed at which a black hole can consume matter, set by the balance between infalling material and outgoing radiation pressure. Eating at this maximum rate for 13 billion years gets you to maybe a few 100 million stellar masses. Impressive, but not enough to explain the billion stellar mass giants we see in the early universe. So something else must be happening. The second possibility is direct collapse. In the early universe, some regions contained enormous clouds of primordial gas. If these clouds collapsed without forming stars, they could fall directly into black holes of 10,000 to 100,000 stellar masses in a single event. No stellar phase, no supernova, just rapid gravitational collapse into something already large. Direct collapse requires special conditions. The gas cloud must be warm enough to avoid fragmenting into stars, which means it needs a nearby source of ultraviolet radiation to prevent cooling. The cloud must also lack heavy elements which promote fragmentation. Computer simulations show this can happen, but only in specific environments. If direct collapse worked, it would produce seed black holes large enough to grow into supermassive ones within the available time. The early universe would have been seeded with monsters, not scraps. A third possibility involves mergers. Intermediate mass black holes, formed through runaway collisions in dense star clusters, could sink toward galactic centers and combine. Each merger doubles the mass, roughly. After enough generations, you reach supermassive territory. This path has support from gravitational wave observations. We know black holes merge. We know the products are larger. The question is whether mergers happened frequently and efficiently enough in the early universe to build supermassive black holes quickly. There might not be a single answer. Different supermassive black holes might have formed through different channels, some from direct collapse, some from super-Eddington accretion, where black holes temporarily consume matter faster than the supposed limit, some from mergers, some from combinations of all three. Resolving this mystery requires seeing further into the past. Telescopes like the James Webb Space Telescope are now probing the first billion years of cosmic history. Early results have revealed surprisingly large black holes shining in the infant universe, challenging our models. Whatever built the supermassive black holes, they have been shaping galaxies ever since. Their gravity influences star formation. Their outflows push gas around. Their presence defines the centers of galactic systems. And at the heart of our own galaxy, one of these ancient machines waits, 26,000 light-years away, hidden behind clouds of dust and gas. A monster sleeps. It does not shine brightly. It does not consume much. But its presence defines the center of everything we call home. Sagittarius A star, the supermassive black hole at the core of the Milky Way, 4 million times the mass of our star, compressed into a region about 14 million miles across, smaller than the orbit of Mercury around our star. For decades, we suspected something massive lurked at the galactic center. Radio observations in the 1970s detected a compact source of emission that seemed far too energetic for any ordinary object. Something powerful and dense sat there, broadcasting signals across the galaxy. Proving it was a supermassive black hole required tracking the stars that orbit it. Beginning in the 1990s, astronomers started monitoring stars near the galactic center using infrared telescopes, which can see through the intervening dust. Year after year, they recorded the positions of these stars, watching them move against the background. What they found was remarkable. One star, called S2, completes an orbit around Sagittarius A star every 16 years. At its closest approach, it sweeps within just a few billion miles of the black hole, moving at nearly 3% the speed of light. The orbit is precise. The mass required to produce such motion is undeniable. 4 million stellar masses, concentrated in a volume no larger than the black hole solution allows. There is no other explanation. Only a supermassive black hole fits the data. More recently, in 2022, the Event Horizon Telescope produced an image of Sagittarius A star itself, not the black hole, which emits no light, but the glowing ring of hot gas surrounding it. The shadow in the center marks the event horizon, the boundary from which nothing returns. That image confirmed what decades of stellar tracking implied. A supermassive black hole sits at the center of our galaxy. It is real, it is there, and it has been anchoring the Milky Way for billions of years. But Sagittarius A star is quiet. Unlike the blazing quasars powered by actively feeding black holes in distant galaxies, our black hole consumes very little. The gas around it trickles in slowly, emitting faint radiation. If the Milky Way's black hole suddenly started feeding at full capacity, it would outshine the entire galaxy. For now, it rests. This was not always the case. Evidence suggests that Sagittarius A star was more active in the past. X-ray echoes bouncing off nearby gas clouds indicate powerful flares occurred within the last few hundred years. Bubbles of hot gas extending above and below the galactic plane, detected by gamma-ray telescopes, suggest enormous outbursts millions of years ago. The black hole wakes occasionally. When enough gas falls in, it lights up. Then it settles down again, waiting for the next meal. Living 26,000 light-years from a 4 million stellar mass black hole might sound frightening, but the distance is so vast that Sagittarius A star poses no threat. Its gravity dominates only within a few light-years of the center. Out here, in the galactic suburbs, we orbit peacefully, held by the combined mass of billions of stars. Still, it is humbling to know that our entire galaxy pivots around a point of darkness, a place where space-time curves so steeply that nothing survives the inward journey. But 4 million stellar masses is modest by supermassive standards. Some black holes make Sagittarius A star look tiny. We are about to meet one that was imaged before our own. On April 10th, 2019, humanity saw the unseeable for the first time. A glowing ring of fire surrounding a dark shadow, the first direct image of a black hole's event horizon. Proof that these objects exist exactly as Einstein's equations predicted over a century ago. The black hole sits at the center of Messier 87, a giant elliptical galaxy roughly 55 million light-years from Earth. It weighs approximately 6.5 billion stellar masses, over 1,500 times more massive than the black hole at the center of our own galaxy. Capturing that image required building a telescope the size of Earth itself. No single telescope could do it. The black hole is so far away that despite its enormous size, it appears incredibly small in the sky. Resolving its shadow required a resolution sharper than any instrument in history. The solution was the Event Horizon Telescope, a network of radio dishes spanning the entire planet, from Hawaii to Spain to the South Pole. By linking these telescopes together and observing the same target simultaneously, astronomers created a virtual telescope with an effective diameter equal to Earth. The technique, called Very Long Baseline Interferometry, combines the data mathematically to achieve resolution impossible for any single dish. Even with this power, the observation was extraordinarily difficult. The team spent over a decade planning. They waited for weather to cooperate at all sites simultaneously. They recorded so much data that it had to be shipped on hard drives because internet transfer would have taken too long. They developed new algorithms to combine the fragmented observations into a coherent image. What emerged from that effort changed astronomy. The image shows a bright ring of emission surrounding a dark central region. The ring is gas, superheated to billions of degrees as it spirals toward the black hole. It glows in radio waves, which is why radio telescopes were necessary. The dark shadow in the center is not the black hole itself. It is the region where light has been captured, unable to escape. The size of that shadow matches the predictions of general relativity almost perfectly. Einstein's equations, written in 1915 without any knowledge of black holes as astrophysical objects, correctly described what we would see a century later. But there is more than confirmation in that image. There is asymmetry. One side of the ring appears brighter than the other. This happens because the gas is orbiting the black hole at tremendous speed, nearly the speed of light on the inner edge. Gas moving toward us has its light boosted by relativistic effects. Gas moving away has its light dimmed. The brightness difference reveals the spin of the accretion flow and hints at the spin of the black hole itself. Messier 87's black hole is almost certainly rotating. Most supermassive black holes probably are. They accumulate angular momentum from the matter they consume over billions of years. A spinning black hole drags space-time around with it, creating effects impossible to observe anywhere else in the universe. 3 years after the first image, the Event Horizon Telescope turned its attention to our own galactic center. Sagittarius A star, though much smaller, was also imaged in 2022. The result was similar: a glowing ring, a dark shadow, confirmation of predictions. But imaging Sagittarius A star was harder in some ways. Because it is so much less massive than Messier 87's black hole, the gas around it orbits faster. Features change in minutes rather than days. The team had to develop new techniques to capture a stable image from rapidly shifting data. Both images represent triumphs of human ingenuity. We cannot visit black holes. We cannot send probes. But we can build instruments capable of seeing across 55 million light-years and resolving objects smaller than our planetary system. Yet even Messier 87's black hole is not the largest. There are monsters that dwarf it. Black holes so massive they challenge the definition of supermassive. At some point, the word supermassive stops feeling adequate. When a black hole contains not millions, not billions, but tens of billions of stellar masses, scientists reach for a new term: ultramassive. The titans among titans, the largest gravitational structures in the universe. These objects blur the line between black hole and cosmic force. The threshold is debated, but many researchers place it at 10 billion stellar masses. Above that, a black hole enters ultramassive territory. Below, it remains merely supermassive. The distinction matters because ultramassive black holes behave differently. Their event horizons are so large that entire star systems could orbit inside. Their influence extends across distances that dwarf even the largest galaxies. Consider scale for a moment. Our star is about 860,000 miles in diameter. A stellar mass black hole of 10 stellar masses would have an event horizon roughly 37 miles across. Sagittarius A star, at 4 million stellar masses, has an event horizon about 14 million miles in diameter, still smaller than the orbit of Mercury. An ultramassive black hole of 40 billion stellar masses would have an event horizon over 750 billion miles in diameter. That is more than 125 times the distance from our star to Pluto. Light would take weeks to cross from one side to the other. You could fit our entire planetary system inside and have room to spare. These are not objects in any ordinary sense. They are regions of dominated space-time, voids where the normal rules of the universe have surrendered to gravity. Where do ultramassive black holes live? They tend to sit at the centers of the largest, oldest galaxies, giant ellipticals, bloated collections of trillions of stars formed from repeated mergers over billions of years. Each merger brought more mass to the central black hole. Each consumed galaxy contributed its own black hole to the final total. Generation after generation of galactic cannibalism built these monsters. The largest confirmed ultramassive black holes exceed 40 billion stellar masses. One candidate, at the center of a galaxy called Holmberg 15A, may hold approximately 40 billion stellar masses. Another, powering the quasar, known as TON 618, might exceed 60 billion. At these masses, the black holes outweigh entire galaxies. The Milky Way contains roughly 200 billion stars, but most of that mass is spread across a disk 100,000 light-years wide. An ultramassive black hole compresses comparable mass into a region you could cross in weeks at the speed of light. But there appears to be a limit. Theoretical calculations suggest that black holes cannot grow indefinitely. At some point, they consume all available matter in their vicinity. Without fresh fuel, growth stops. The maximum possible mass depends on the age of the universe and the availability of gas. But estimates suggest black holes cannot exceed about 100 billion stellar masses through normal accretion. Some researchers believe we have already found black holes near this limit. If true, the largest black holes in the universe today are as large as they will ever get. They have reached the end of their growth, waiting in darkness for the slow decline that will eventually claim them. But before they fade, they put on quite a show. One ultramassive black hole shines brighter than everything else in the known universe. Imagine an object so bright that it outshines 140 trillion stars. Imagine that brilliance pouring from a region smaller than our planetary system. Imagine that this beacon of light marks the location of one of the most massive black holes ever measured. This is TON 618, a quasar, a monster, a challenge to everything we thought we understood about cosmic limits. Located roughly 10.8 billion light-years from Earth, TON 618 appears as little more than a point of light in most telescopes. For decades after its discovery in 1957, astronomers thought it was a peculiar blue star in our own galaxy. Only later did they realize the truth. This object lies at cosmological distances, and its apparent brightness means it must be releasing energy on a scale that defies imagination. The black hole powering TON 618 has an estimated mass of 40 to 66 billion stellar masses, depending on the measurement technique used. Even the lower estimate makes it one of the heaviest black holes known. The higher estimate would place it among the absolute largest. But mass alone does not make TON 618 remarkable. What sets it apart is how actively it feeds. The black hole is surrounded by a disk of superheated gas spiraling inward. As this material falls, it releases gravitational energy as light, lots of light. TON 618 shines with a luminosity equivalent to 140 trillion stars like ours. That is more light than most galaxies produce combined. In fact, the quasar is so bright that we cannot see the galaxy surrounding it. The glare overwhelms everything. Whatever stars orbit in TON 618's home galaxy are invisible against the brilliance of the central engine. We know the galaxy must exist. Every supermassive black hole inhabits a galaxy, but this one hides its host completely. The event horizon of TON 618 stretches across a staggering distance. If the mass is 66 billion stellar masses, the event horizon spans over 1,300 astronomical units. An astronomical unit is the distance from Earth to our star, roughly 93 million miles. The black hole's boundary would extend more than 40 times farther from the center than Neptune orbits from ours. Light takes days to cross from one side of this event horizon to the other. You could fit dozens of complete planetary systems inside the boundary and still have room. Yet, for all its size, TON 618 is unreachable. The light we see today left that region over 10 billion years ago. We are observing the ancient universe, a time when galaxies were young and black holes were growing rapidly. Whatever TON 618 looks like now, we will not know for another 10 billion years, when light from the present finally arrives. This raises a humbling thought. Every observation of distant quasars is a look into the past. The objects we study may have changed dramatically, or even ceased to exist in their current form. We are cosmic archaeologists, sifting through ancient light for clues about how the universe assembled itself. TON 618 represents an extreme, a black hole near the upper limit of possible mass, feeding near the upper limit of possible rate, shining near the upper limit of possible brightness. It is the universe pushed to the edge, but brightness requires fuel. And to understand how black holes shine, we need to examine what happens to matter as it approaches the point of no return. The accretion disk is where energy is born from destruction. Nothing falls straight into a black hole. Matter spirals. It swirls. It forms a flattened disk of destruction that converts mass into the most intense light in the universe. This is the accretion disk. and understanding it explains how invisible black holes become the brightest objects in existence. Here is the problem matter faces. When gas falls toward a black hole, it carries angular momentum, spin, motion perpendicular to the direction of fall. This angular momentum prevents direct infall. Instead of plunging straight in, the gas settles into orbit around the black hole, forming a disk. Inside this disk, particles collide. Friction builds. Inner regions orbit faster than outer regions, and the difference creates shear. Energy transfers outward. Angular momentum follows. The innermost gas gradually loses the momentum, keeping it aloft, and sinks closer to the event horizon. As gas falls deeper into the gravitational well, it accelerates. Particles move faster and faster. Collisions become more energetic. Temperature rises. Near the inner edge of the disk, temperatures reach millions or even billions of degrees. Gas at these temperatures glows intensely, emitting radiation across the entire electromagnetic spectrum. This is how black holes shine, not from the black hole itself, which emits nothing, from the destruction of matter trying to fall in. The energy released comes from gravity, extracted as material spirals downward, and gravity is efficient. Accretion can convert up to 32% of infalling mass into energy. Compare that to nuclear fusion in stars, which converts less than 1%. This efficiency explains quasars. A supermassive black hole consuming even modest amounts of gas produces tremendous luminosity. Feed it enough material, and it outshines every star in its galaxy combined. The structure of an accretion disk is layered. The outer regions are cooler, emitting infrared and visible light. Moving inward, temperature rises, and the emission shifts to ultraviolet and X-rays. The innermost region, just outside the event horizon, produces the highest energy radiation. Some disks generate gamma rays from processes near the central black hole, but the disk is not a calm structure. It is turbulent. Magnetic fields thread through the gas, tangling and reconnecting. Instabilities develop. Clumps of material fall inward unpredictably. The brightness of an accreting black hole can fluctuate over days, hours, or even minutes as conditions in the disk change. There is another feature worth noting. Above and below the disk, material can be launched outward in powerful winds. Radiation pressure from the glowing disk pushes on gas, accelerating it away from the black hole. These outflows carry energy and matter back into the surrounding galaxy, influencing star formation and chemical evolution. In the most extreme cases, something even more dramatic happens. Jets of material, accelerated to nearly the speed of light, shoot perpendicular to the disk. These jets can extend for millions of light years, carrying energy far beyond the galaxy that produced them. We will explore jets soon, but first, understand that accretion disks are the engines of active black holes. Without infalling matter, a black hole is invisible. With a steady supply of gas, it becomes a beacon visible across the observable universe. The brightest of these beacons have a special name: quasars, the lighthouses at the edge of time. When astronomers first detected them in the 1960s, nobody knew what they were: point sources of radio waves with no obvious optical counterpart. Then they found faint blue objects at those positions. Objects that looked like stars, but had spectra unlike anything seen before. They called them quasi-stellar radio sources, quasars for short, and they would turn out to be the most luminous, sustained objects in the universe. The breakthrough came in 1963, when astronomer Martin Schmidt measured the spectrum of a quasar called 3C273. He found familiar patterns, hydrogen emission lines, but shifted dramatically toward longer wavelength. The only explanation was that the object was moving away from us at tremendous speed, carried by the expansion of the universe. That meant it was far away, very far. At that distance, its apparent brightness implied an absolute luminosity beyond anything previously imagined, a single object producing more light than 100 normal galaxies. How was this possible? The answer was accretion onto a supermassive black hole. Quasars are active galactic nuclei, the central regions of galaxies where supermassive black holes are feeding aggressively. Gas funnels inward, forms an accretion disk, heats to extreme temperatures, and radiates at enormous power. The black hole itself is invisible. The disk is blinding. At their peak, quasars shine with luminosities exceeding 10 trillion stellar luminosities. They can be seen across most of the observable universe. The most distant quasars detected lie over 13 billion light-years away, their light having traveled for nearly the entire history of the cosmos to reach us. This makes quasars valuable tools for understanding the early universe. Because they are so bright, we can study them even at extreme distances. Their spectra reveal information about the gas between us and them. By observing how light is absorbed during its journey, astronomers map the distribution of matter across billions of years of cosmic time. But quasars are not eternal. They require fuel. A supermassive black hole can only sustain quasar-level luminosity as long as gas keeps falling in. Eventually, the supply runs low. The disk thins. The brightness fades. The quasar era ends. Most quasars existed in the distant past, when the universe was younger and galaxies were still assembling. Gas was abundant. Collisions between galaxies funneled fresh material towards central black holes. The universe blazed with quasar light. Today, quasars are rare in the nearby universe. Most supermassive black holes have settled into quiet retirement. Like Sagittarius A star, they still exist. They still anchor their galaxies. But without gas to consume, they no longer shine. Occasionally, something stirs them awake. A star wandering too close gets torn apart, providing a temporary meal. A collision with another galaxy delivers fresh gas. For a brief time, the black hole flares back to activity before settling down again. Quasars showed us that black holes are not passive objects. They can dominate their environments. They can shine across the universe. They can influence the evolution of galaxies over billions of years. But some quasars are more dangerous than others. Some point their most energetic emissions directly at Earth. We call those blazars, and they are among the most violent objects we can observe. Imagine staring down the barrel of a cosmic cannon, a beam of particles traveling at nearly the speed of light, aimed straight at your location across billions of light years. The energy output fluctuating wildly, doubling or halving in brightness over just a few days. This is a blazar, and it is one of the most extreme phenomena in the known universe. Blazars are a special type of active galactic nucleus. Like quasars, they involve supermassive black holes surrounded by accretion disks. But blazars have something additional: powerful jets of material shooting outward from the poles of the black hole. And by chance, one of those jets points directly toward Earth. This alignment changes everything we observe. When a jet travels toward us at close to light speed, relativistic effects dramatically boost its apparent brightness. Light emitted from the approaching jet gets compressed in wavelength and amplified in intensity. What might appear as a modest emission from the side becomes a blinding beacon when viewed head-on. Blazars are among the most variable objects in the sky. Their brightness can change significantly over hours or days. Some have flared by factors of 10 or more in less than a week. This variability comes from instabilities in the jet, clumps of material moving through turbulent magnetic fields, shocks propagating along the flow. The spectrum of a blazar is equally extreme. Unlike quasars that show clear emission lines from gas near the black hole, many blazars have nearly featureless spectra. The jet emission dominates so completely that it drowns out the light from the accretion disk and surrounding gas. We see only the jet, blazing toward us like a searchlight. Blazars emit across the entire electromagnetic spectrum: radio waves from the extended jet, infrared and visible light from particles spiraling in magnetic fields, X-rays from the hottest regions near the black hole, and gamma rays the most energetic form of light, produced by particles accelerated to tremendous energies in the jet. The gamma-ray emission is particularly important. Blazars are among the brightest gamma-ray sources in the sky. Space telescopes, like Fermi, monitor them continuously, tracking their flares and trying to understand what physical processes can accelerate particles to such extremes. There is evidence that blazars also produce something beyond light. High-energy neutrinos, ghostly particles that barely interact with matter, have been linked to blazar flares. In 2017, a neutrino detected by the Ice Cube Observatory in Antarctica was traced back to a blazar called TXS 0506 plus 056. This made blazars candidates for producing some of the most energetic particles in the universe. We do not fully understand how jets accelerate material to such speeds. Magnetic fields clearly play a role. The rotation of the black hole may contribute through frame dragging, twisting space-time itself into the magnetic structure. Computer simulations can reproduce some features, but the detailed physics remains an active area of research. What we know is that blazars represent a perfect storm of extremes: a feeding supermassive black hole, a powerful relativistic jet, and an alignment that points all that energy directly at us. Fortunately, the nearest blazars are hundreds of millions of light years away. We observe, but we are not harmed. The jets themselves, however, deserve closer examination. They are among the largest structures any black hole creates. Black holes are supposed to be traps. Nothing escapes. Not light, not matter, not information. And yet, surrounding some of the most actively feeding black holes are jets of material shooting outward at 99% the speed of light, extending millions of light years into intergalactic space. How is this possible? The answer is that the jets do not come from inside the black hole. They form outside the event horizon, in the violent environment where infalling matter meets extreme magnetic fields. Nothing violates the rule that what enters cannot leave. The jets are escape routes for material that never quite fell in. Here is what we think happens. As gas spirals toward a black hole through an accretion disk, it carries magnetic fields tangled within it. These fields get compressed and amplified by the differential rotation of the disk. Near the black hole, the magnetic field lines become twisted into tight spirals aligned with the rotation axis. Material near the poles of the disk can follow these field lines upward, away from the disk plane. Instead of falling into the black hole, it gets channeled along the magnetic structure and accelerated outward. The energy for this acceleration comes from the rotation of the disk and possibly from the spin of the black hole itself. The result is a jet, a narrow beam of plasma, electrons, and positrons, and perhaps heavier particles, moving at relativistic speeds. The jet remains collimated, focused into a tight stream by the magnetic fields that created it. Without those fields, the material would spread out and dissipate. With them, it stays coherent across distances that dwarf galaxies. Some jets extend for millions of light years. The galaxy Messier 87, home to the black hole we imaged in 2019, has a jet visible in optical telescopes, stretching nearly 5,000 light-years from the core. In radio observations, the structures extend much farther, inflating enormous lobes of hot gas in the surrounding space. These lobes represent the accumulated energy of millions of years of jet activity. Material ejected from the black hole eventually slows down as it plows into the thin gas between galaxies. It spreads out, forming vast bubbles of energized plasma that glow in radio waves. Some lobes span more than 1 million light-years, making them among the largest single structures in the universe. Jets influence their environments profoundly. The energy they carry heats surrounding gas, preventing it from cooling and forming stars. In galaxy clusters, jets from central black holes can regulate the entire thermal state of the system. Without jets, the gas would cool, collapse, and form huge numbers of new stars. With jets, the gas stays hot and diffuse. This feedback loop connects the smallest scales, the immediate vicinity of a black hole, to the largest, the evolution of entire galaxy clusters. A single object, smaller than our planetary system, controlling the fate of millions of light years of space. Not all actively feeding black holes produce jets. The conditions seem to require both rapid spin and the right magnetic field geometry. Maybe 30% of active galactic nuclei are radio loud, meaning they have powerful jets. The rest are radio quiet, with little or no jet emission. Understanding why some black holes jet and others do not remains an open question. Spin probably matters. Magnetic field strength probably matters. The details remain to be worked out. But jets remind us that black holes are not just endpoints. They are engines, generators of structure on cosmic scales. And near these engines, time itself behaves strangely. Stand near a black hole, and the clocks you carry will tick normally. You will age at the same rate you always have. A second will feel like a second. A year will feel like a year. Nothing seems unusual from your perspective. But to someone watching from far away, you have become a statue, frozen at the edge of eternity. Time itself has slowed for you, stretching every moment into infinity as you approach the event horizon. This is gravitational time dilation, and it is not science fiction, it is confirmed physics. Einstein's general theory of relativity describes gravity not as a force pulling objects together, but as curvature in the fabric of space-time. Mass bends space-time. The more mass concentrated in a region, the greater the bending, and the greater the bending, the slower time passes relative to regions with less curvature. We measure this effect constantly. Satellites in orbit experience slightly weaker gravity than objects on Earth's surface. As a result, their clocks tick slightly faster than ground-based clocks. The difference is tiny, a few microseconds per day, but it is real and measurable. GPS systems must account for it to maintain accuracy. Near a black hole, this effect becomes extreme. As you approach the event horizon, space-time curvature increases dramatically. Time slows compared to distant observers. At the horizon itself, the dilation becomes infinite. From the perspective of someone watching from a safe distance, you never actually cross the event horizon. Your image freezes at the boundary, redshifting into invisibility as the light you emit stretches to longer and longer wavelengths. You would not notice any of this. From your perspective, you fall through the horizon in finite time. Clocks you carry keep normal pace. But if you could look back at the universe outside, you would see something strange. Stars moving faster, galaxies evolving, the universe aging rapidly as you drift inward. Time outside accelerates while you fall. The mathematics behind this is solid. The predictions match observations in every test we have been able to perform. Gravitational time dilation is as confirmed as any phenomenon in physics. But there is a twist that makes black holes particularly strange. Inside the event horizon, space and time exchange roles in a sense. The direction toward the singularity, which was purely spatial outside, becomes time-like inside. Falling toward the center is no longer moving through space. It is moving through time. The singularity is not a place. It is a moment in your future, and reaching it is as inevitable as tomorrow. This is difficult to visualize because our intuition is built for ordinary space-time. Near a black hole, that intuition fails. The geometry is too extreme. Concepts like distance and duration blur together in ways that resist simple description. What we can say is that time near a black hole is not absolute. It depends on where you are and how you are moving. The universe does not tick at a single rate. It flows differently in different places, and near a black hole, that flow becomes dramatically warped. For observers outside, watching infalling matter approach the horizon, the matter never seems to arrive. It accumulates at the edge, red-shifting away into darkness. But the black hole still grows. Mass still enters. Energy still adds to the total. The event horizon is a one-way door. and time is the guard that never lets anyone see it close. Yet black holes do not just trap matter, sometimes they tear it apart first. What happens when an entire star gets too close? It happens silently, across millions of light years, in galaxies we barely notice. A star wanders too close to a supermassive black hole. The gravitational pull on one side of the star overwhelms the pull on the other. The star stretches, it tears. In a matter of hours, what was once a nuclear furnace becomes a river of debris spiraling toward the event horizon. Astronomers call these tidal disruption events, and we have witnessed dozens of them. The physics is the same spaghettification we discussed earlier, but scaled up to stellar sizes. A star has significant internal gravity holding it together, but that gravity is finite. Approach close enough to a supermassive black hole, and the tidal forces exceed the star's own binding energy. The star loses the battle and shreds apart. Not all of the star falls in immediately. Roughly half the debris remains bound to the black hole, settling into an elongated accretion disk. The other half is flung outward, escaping back into space. Over the following weeks and months, the bound material spirals inward, lighting up as it approaches the event horizon. This creates a flare, a sudden brightening of the galactic center that can be detected across billions of light years. The flare rises quickly as debris begins to accumulate, then fades slowly as the material drains into the black hole. The characteristic light curve lets astronomers identify tidal disruption events among the many other transient phenomena in the sky. In October 2019, telescopes caught a tidal disruption event remarkably close by cosmic standards. The event, labeled AT 2019 KIS, occurred just 215 million light-years away. The proximity allowed unprecedented observations. Astronomers watched the star being torn apart in real time. They tracked the debris forming a disk. They measured the outflows of material launched by radiation pressure. For the first time, they saw the complete sequence from disruption to accretion in high detail. The data confirmed theories that had been developed over decades. The flare behavior matched predictions from computer simulations. The temperatures, luminosities, and timescales all aligned with models of stellar disruption by supermassive black holes. But there were surprises too. The outflows were stronger than expected. A significant fraction of the debris was not falling in but blowing outward. Some of the material formed a wind escaping the system at high speed. This matters for understanding how black holes grow. If a substantial portion of infalling matter gets expelled, black holes eat less efficiently than simple models suggest. Tidal disruption events become less effective at feeding the central monster. How often do these events occur? Estimates vary, but a typical galaxy might experience a tidal disruption roughly every 10,000 to 100,000 years. That sounds rare, but there are billions of galaxies in the observable universe. At any moment, thousands of stars are being shredded by black holes across the cosmos. Most of these events go unnoticed. The galaxies are too far away, the flares too faint. Our surveys cannot catch them all, but the detection rate is increasing as telescopes improve. Upcoming facilities will find tidal disruptions by the thousands, turning a rare curiosity into a powerful tool for studying black holes and their environment. Every disruption is a tragedy for the star involved, but for astronomers, each flare is a gift, a signal from the edge of a black hole, revealing the dynamics of matter under extreme gravity. The universe offers other signals from black holes too. Not light, something stranger. Ripples in space-time itself. Einstein predicted them a century ago. He doubted we would ever detect them. They were too faint, he thought, too subtle. The technology to sense them seemed impossibly beyond reach. He was wrong about our capabilities. In 2015, we heard gravitational waves for the first time, and black holes were singing. Gravitational waves are ripples in space-time, produced when massive objects accelerate. Every orbiting planet, every spinning star, every moving mass creates them. But most sources are so weak that the waves are undetectable. Only the most violent events in the universe produce gravitational waves strong enough to measure. Black hole mergers are among those events. When two black holes spiral together, they lose orbital energy by radiating gravitational waves. The closer they get, the faster they orbit. The faster they orbit, the stronger the waves they emit. In the final seconds before merger, the system releases more gravitational wave power than all the stars in the observable universe combined. This power radiates outward at the speed of light, stretching and squeezing space-time as it passes. By the time the waves reach Earth from a distant merger, they have spread across billions of light-years and weakened enormously. The distortion they produce is almost impossibly small. A ripple from a typical black hole merger changes the length of a 4-kilometer detector arm by less than the width of a proton. Detecting such a tiny signal required decades of engineering. The solution was the Laser Interferometer Gravitational Wave Observatory, known as LIGO. Two facilities, one in Louisiana and one in Washington State, each housing an L-shaped vacuum tunnel with 4-kilometer arms. Laser beams bounce back and forth along the arms, and interference patterns reveal minuscule changes in length. When a gravitational wave passes, it stretches one arm while compressing the other. The laser interference pattern shifts. The shift is recorded, and if both detectors see the same pattern within the light travel time between them, we know a gravitational wave has arrived. The precision required is staggering. The detectors must isolate against earthquakes, traffic vibrations, thermal fluctuations, and countless other noise sources. The laser beams must be perfectly aligned. The mirrors must be suspended with exquisite stability. After decades of work, the system achieved the necessary sensitivity. And on September 14, 2015, a signal appeared. A rising chirp in the data, frequency increasing, amplitude growing, then a sudden peak and fade. The entire event lasted less than 0.2 of a second. Analysis revealed two black holes, about 36 and 29 stellar masses, spiraling together and merging roughly 1.3 billion light-years away. The collision released energy equivalent to about 3 stellar masses, all in the form of gravitational waves. In that fraction of a second, the merging black holes radiated more power than every star in the observable universe produces in light. We heard it. Across more than 1 billion light-years, across more than 1 billion years of time, we captured the vibration of space-time from two black holes becoming one. That first detection opened a new era in astronomy. We no longer depend on light alone. We can listen to the universe in gravity. And the mergers we have detected since have grown ever more extreme. The signal arrived on September 14, 2015, at exactly 9:50 and 45 seconds Coordinated Universal Time. 7 milliseconds later, it reached the second detector. The waveform matched theoretical predictions for two black holes spiraling together and colliding. After a century of prediction, gravitational waves were finally confirmed, and black holes were the source. The event, labeled GW150914 for the date of detection, told us remarkable things about the objects involved. Before the merger, the two black holes had masses of about 36 and 29 stellar masses. Both were likely spinning. They had been orbiting each other for millions of years, gradually spiraling closer as gravitational waves carried away energy. In the final moments, the pace accelerated dramatically. The black holes completed the last several orbits in less than a second. They moved at roughly half the speed of light. The gravitational wave frequency climbed from 35 to 250 cycles per second, a rising tone that scientists converted to audible sound and called the chirp. Then they touched. The event horizons merged. The combined black hole shuddered, briefly distorted into a lumpy shape, and rang like a struck bell as it settled into equilibrium. This ring-down phase emitted final gravitational waves before the new black hole became silent. The merger produced a single black hole of about 62 stellar masses. Notice the math. 36 plus 29 equals 65, not 62. The missing 3 stellar masses did not disappear. They converted to energy, pure gravitational wave energy, radiated outward at the speed of light. 3 stellar masses converted to energy in a fraction of a second. Einstein's famous equation describes the conversion rate. Energy equals mass times the speed of light squared. 3 stellar masses translates to roughly 5 times 10 to the 47th joules. For comparison, our star will take 10 billion years to produce that much energy, all of it released in less than a second. The detection confirmed multiple predictions. General relativity survived another test. The waveform matched theoretical templates derived from Einstein's equations. Black holes exist as predicted. They merge as predicted. They produce gravitational waves as predicted. But the discovery also raised new questions. The masses involved were larger than expected. Before this detection, astronomers thought stellar black holes typically weighed less than 20 stellar masses. Finding 2 above 30 suggested that massive black holes are more common than believed, or that they form through processes we did not anticipate. Since that first detection, the LIGO and Virgo collaborations have observed hundreds of black hole mergers. Each event teaches us something new about black hole populations, how they form, how they pair up, how they merge, a census of invisible objects, counted by the ripples they make in space-time. The announcement came on February 11, 2016, a press conference that made headlines worldwide. The scientists who built LIGO received the Nobel Prize in Physics the following year. But one first detection was only the beginning. The mergers we have found since have pushed the boundaries of what we thought possible. One recent event set records that challenge our understanding entirely. On November 23, 2023, a signal arrived that pushed gravitational wave astronomy to its limits. The waveform suggested something unprecedented. 2 enormous black holes, each roughly 100 stellar masses, spiraling together and colliding to form a monster of approximately 225 stellar masses. The detection, labeled GW231123, shattered previous records and raised immediate questions. Black holes this massive should not exist according to standard stellar evolution models. Remember the pair instability gap? Stars that would produce black holes between roughly 50 and 130 stellar masses are supposed to destroy themselves completely. The explosion unbinds everything. Nothing remains. Yet here were 2 black holes with masses right in that forbidden zone, merging into something even larger. Several explanations are possible. The most likely is hierarchical merging. These black holes were not first-generation stellar remnants. They were themselves products of earlier mergers. Smaller black holes combined in the past, producing objects in the gap, and those products then found each other and merged again. This scenario requires dense environments where black holes can meet repeatedly. Globular clusters qualify. Galactic nuclei qualify. Any region where black holes accumulate and encounter each other over billions of years could produce hierarchical mergers. Another possibility involves unusual stellar progenitors. Stars in the early universe, or stars in metal-poor environments, might evolve differently. They might retain more mass before collapse. They might find ways around pair instability that our models do not yet capture. The forbidden zone might have exceptions we need to discover. The detection also revealed extreme spins. Both black holes appeared to be rotating rapidly, near the maximum rate allowed by general relativity. Highly spinning black holes are hard to produce from single stellar collapses, but arise naturally from mergers. Again, this supports the hierarchical interpretation. Extracting information from the signal required sophisticated analysis. The waveform was complex, influenced by the rapid spins and possible precession of the orbital plane. Standard templates struggle with such extreme parameters. Researchers developed new methods to interpret the data, pushing theoretical tools along with observational ones. Even with careful analysis, uncertainties remain large. The masses could be somewhat higher or lower than the best estimates. The spin measurements have significant error bars. Future observations of similar events will help pin down the physics. What seems clear is that black hole populations are more diverse than we expected. Some black holes inhabit the mass gap that theory declared forbidden. Some reach into intermediate mass territory through repeated mergers. The boundary between stellar and supermassive black holes is messier than the clean categories we invented. This particular merger released roughly 5 to 10 stellar masses of energy as gravitational waves. A burst of space-time rippling outward at light speed, carrying information about one of the most extreme collisions the universe has produced. The signal traveled roughly 5 billion light-years before reaching our detectors. 5 billion years. That means this merger happened when our star had not yet ignited. Earth did not exist. The gravitational waves traveled through space while our planetary system formed, while life evolved, while civilizations rose and fell. And then, one autumn day, in 2023, they arrived. We heard them, we recorded them, we analyzed them. And now we know that black holes can grow larger than we imagined, building themselves merger by merger through cosmic time. But growth is not the only fate for black holes. Over unimaginably long timescales, even the mightiest black holes will shrink. Slowly, inexorably, until nothing remains. Black holes seem eternal. Once formed, nothing escapes. Mass can only accumulate, never diminish. The event horizon marks a permanent boundary, forever dividing the universe from what lies within. This picture is incomplete. In 1974, physicist Stephen Hawking demonstrated that black holes are not truly black. They emit radiation, slowly, faintly, but inevitably. Given enough time, a black hole will radiate away all its mass and vanish completely. This discovery is called Hawking radiation, and it connects black holes to quantum mechanics in ways that still puzzle physicists today. Here is the basic idea, though the common explanations are often misleading. Near the event horizon, space-time is intensely curved. Quantum field theory describes how particles and fields behave in curved space-time, and the results are surprising. A detector near the horizon would register a thermal bath of particles even in what seems like empty space. The curvature itself creates something that looks like heat. This thermal radiation carries energy away from the black hole. The energy has to come from somewhere, and it comes from the black hole's mass. Slowly, the black hole loses mass to this emission. As it shrinks, it gets hotter. As it gets hotter, it radiates faster. The process accelerates over time. But do not expect to watch a black hole evaporate. The timescales are absurdly long. A stellar mass black hole of 10 stellar masses would take approximately 10 to the 67th power years to evaporate. That number is so large, it defies comprehension. The current age of the universe is roughly 14 billion years, or about 10 to the 10th power years. A stellar black hole will last for more than 10 to the 56 times longer than the universe has existed so far. Supermassive black holes live even longer. A black hole of 1 billion stellar masses would take around 10 to the 99th power years to evaporate. The universe will have expanded, cooled, and faded into darkness long before these giants begin to noticeably shrink. Only the smallest hypothetical black holes would evaporate on observable timescales. A black hole with the mass of a mountain might evaporate in billions of years. One with the mass of a large asteroid might take only millions. At the very end, when the black hole has shrunk to a tiny fraction of its original mass, the radiation becomes intense and the final evaporation happens rapidly. The endpoint is unknown. Hawking's original calculation suggests the black hole should vanish entirely in a final burst of particles. But the calculation breaks down when the black hole approaches the Planck scale, where quantum gravity effects become important. What happens in those final moments remains one of the deepest mysteries in physics. Hawking radiation has never been directly observed. The emission from any astrophysical black hole is far too weak to detect against the cosmic microwave background. Even the nearest stellar black hole would emit Hawking radiation trillions of times fainter than anything our instruments can sense. Yet the theoretical implications are profound. Hawking radiation means black holes have temperature, entropy, thermodynamic properties. They are not just geometric features of space-time, but physical objects that obey the laws of thermodynamics. This connection between gravity, quantum mechanics, and thermodynamics is one of the deepest insights in modern physics. Understanding it fully may require a complete theory of quantum gravity that we do not yet possess. But there is another implication of Hawking radiation that troubles physicists even more. What happens to the information that falls in? Every object that enters a black hole carries information. The arrangement of atoms, the quantum states of particles, the history encoded in structure. When a book falls into a black hole, all the words it contained go with it. When a person falls in, every memory, every thought, every detail of their existence disappears beyond the event horizon. Physics has a rule about information. It cannot be destroyed. The laws of quantum mechanics are unitary, meaning that the total information in a closed system is preserved over time. You can scramble information, encrypt it, spread it out, but you cannot erase it. Given complete knowledge of the present, you could in principle reconstruct the past. Black holes seem to violate this rule. According to Hawking's original calculation, the radiation emitted by a black hole is thermal, random. It carries no information about what fell in. A black hole formed from a collapsing star and a black hole formed from an equal mass of encyclopedias would emit identical Hawking radiation. The radiation does not remember its origin. If the black hole eventually evaporates completely, what happened to the information? The objects that fell in are gone. The black hole is gone. The radiation carried nothing meaningful. The information has apparently vanished from the universe. This is the black hole information paradox, and it has occupied theoretical physicists for over 50 years. Some proposed that information is simply lost. The universe does not preserve everything. Black holes are exceptions to the rules of quantum mechanics. Hawking initially held this view, but most physicists find this deeply troubling. The principles that demand information preservation are foundational to quantum mechanics. Abandoning them would undermine the entire framework that describes particle physics, chemistry, and everything built on quantum theory. Other researchers propose that information escapes gradually, encoded subtly in the Hawking radiation. The radiation might not be perfectly thermal. Tiny correlations between emitted particles, imperceptible to any measurement, might carry the missing information. As the black hole evaporates, the information slowly leaks out, scrambled almost beyond recognition but technically preserved. This possibility has gained traction in recent years. Calculations using ideas from string theory and holography suggest that information can escape. The details involve deep mathematics, but the conclusion is encouraging. Quantum mechanics might survive intact. A third possibility involves remnants. Perhaps black holes do not evaporate completely. Perhaps they shrink to some minimum size and stop, leaving behind a tiny object that contains all the information. These remnants would be incredibly small and contain enormous amounts of encoded data. Remnants have problems too. If every black hole leaves a remnant, and remnants can hold arbitrary amounts of information, strange consequences follow for how quantum fields behave in their presence. The paradox remains unresolved. We do not know with certainty how information behaves in the presence of black holes. Solving this puzzle likely requires understanding quantum gravity, the merger of quantum mechanics and general relativity that has eluded physicists for decades. Black holes are not just cosmic objects, they are laboratories for the most fundamental questions in physics. Where gravity meets quantum mechanics, our understanding breaks down, and at that boundary, other strange possibilities emerge, objects that might be the opposite of black holes, theoretical time reversals of everything we have discussed. If a black hole is a region that nothing can escape, a white hole is a region that nothing can enter. Matter and light can only flow outward. The event horizon works in reverse. Instead of a cosmic drain, a cosmic fountain. White holes emerge from the mathematics of general relativity. They are solutions to Einstein's equations just as valid as black hole solutions. Time reversal symmetry demands their existence, at least on paper. But whether white holes actually exist in our universe is unknown. Probably not. Here is the problem. A black hole forms through natural processes. Stars collapse. Matter accumulates. Gravity overwhelms all opposition. We understand how black holes come to be. A white hole would require the opposite, matter spontaneously emerging from a boundary that nothing can cross. No known physical process creates this. White holes do not form from stellar evolution. They do not result from mergers. They have no origin story in standard cosmology. Some theorists have speculated that white holes might be the other end of black holes. The idea appears in science fiction regularly. Fall into a black hole, emerge from a white hole somewhere else. A tunnel through space-time connecting distant regions. This is the concept behind wormholes, which we will discuss shortly. But the connection is problematic. Mathematical analysis shows that the bridge between a black hole and a hypothetical white hole would be unstable. It would collapse before anything could traverse it. The transit time would be zero. Useful transportation seems impossible. Another speculation connects white holes to the Big Bang itself. The universe began in an extremely hot, dense state, with matter expanding outward. This resembles a white hole in some ways, a region where matter can only flow out, where nothing can enter. Perhaps the Big Bang was a white hole event, the universe emerging from a reversed horizon. This idea is poetic but difficult to test. The conditions at the Big Bang are extreme enough that our theories do not apply reliably. We cannot observe what happened at time zero. We can only infer from what came after. There have been proposals to look for white holes observationally. If one existed, it would spew matter and energy into space. The signature might resemble certain explosive phenomena, gamma-ray bursts or fast radio bursts, that we observe but do not fully understand. So far, no confirmed detection of a white hole has been made. The candidates have other explanations that do not require such exotic objects. Most physicists regard white holes as mathematical curiosities rather than physical realities. They satisfy the equations but violate plausibility. Nature creates black holes. Nature does not seem to create white holes. Still, the concept illuminates the structure of general relativity. The equations do not forbid white holes. They do not demand them either. The universe seems to choose black holes over their time-reversed counterparts. But the connection between black holes and white holes leads to a more famous idea: tunnels through space-time, shortcuts between distant points, passages that might, under the right conditions, permit travel across unimaginable distances. We call them wormholes, and they remain among the most tantalizing possibilities in theoretical physics. In 1935, Albert Einstein and Nathan Rosen published a paper exploring solutions to the equations of general relativity. They discovered that a black hole solution could be extended mathematically to connect to another region of spacetime, a bridge, a tunnel. They were not trying to invent science fiction. They were trying to understand the fundamental nature of particles and fields. But what they found has captured imaginations ever since. The Einstein-Rosen bridge, as it came to be known, connects the interior of a black hole to something else. In the simplest case, that something else is another black hole, possibly in a different part of the universe, possibly in a different universe entirely. The bridge forms a throat, a narrow passage where the two regions meet. Physicist John Wheeler later popularized the term wormhole, noting that the structure resembles a worm's path through an apple. Instead of traveling across the surface, you burrow through. The appeal is obvious. If wormholes existed and were traversable, they might allow travel between distant points without crossing the space between. A shortcut through the fabric of reality, instant connection across billions of light years. But there are serious problems. First, the original Einstein-Rosen bridge is not traversable. Further analysis showed that the throat collapses faster than anything can pass through. Even light cannot make the transit. The bridge opens and closes in an instant, permitting no crossings. Second, keeping a wormhole open would require exotic matter with negative energy density. Normal matter has positive energy. It would cause the throat to collapse, not stabilize. Negative energy matter, if it exists at all, has never been observed in the quantities needed. Quantum field theory permits tiny amounts in certain configurations, but nothing remotely sufficient for a macroscopic wormhole. Third, traversable wormholes might create paradoxes. If a wormhole connected two regions at different times as well as different places, it could potentially allow travel to the past. This raises all the familiar problems of causality, going back in time and changing events that led to your own journey. The physics of time travel remains deeply uncertain. Despite these obstacles, wormholes continue to fascinate researchers. Some have explored how to construct stable, traversable wormholes within the rules of general relativity. The required exotic matter remains a barrier, but the theoretical framework exists. If we ever discovered a source of sufficient negative energy, the engineering might follow. Recent work has also connected wormholes to quantum entanglement. The ER equals EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests that entangled particles might be connected by microscopic wormholes, not traversable bridges, not shortcuts for travel, but a deep link between quantum mechanics and space-time geometry. This idea is speculative but provocative. It hints that the fabric of space-time might be stitched together by quantum connections. Black holes and entanglement and wormholes might all be aspects of a single underlying reality that we are only beginning to glimpse. For now, wormholes remain theoretical. No observational evidence supports their existence. The energy requirements seem impossible. The stability conditions appear unachievable, but the equations permit them, and physics has a history of permitting things that later turn out to be real. There is one more type of black hole we have not yet discussed. Objects that may have formed before stars existed, before galaxies assembled, in the first heartbeat of the universe itself, relics from the beginning. Less than 1 second after the Big Bang, the universe was unrecognizable. No stars, no galaxies, no planets, just an expanding sea of energy and matter, hotter and denser than anything we can replicate today. In that brief, violent era, black holes might have formed through a process completely different from stellar collapse. These hypothetical objects are called primordial black holes, and if they exist, they have been drifting through the cosmos for nearly 14 billion years. The idea emerged in the 1960s and 70s. Physicist Stephen Hawking explored the possibility extensively. The reasoning goes like this. In the early universe, matter was not smoothly distributed. Tiny fluctuations existed, regions slightly denser than their surroundings. If any fluctuation was dense enough, gravity could overwhelm expansion and collapse that region directly into a black hole. No star needed, no supernova, just pure gravitational collapse in the first fraction of a second. The mass of these primordial black holes would depend on when they formed. Earlier formation, when the universe was denser, would produce smaller black holes. Later formation, when things had expanded and cooled somewhat, would produce larger ones. The range spans from microscopic objects lighter than a grain of sand to black holes thousands of times more massive than our star. This range is intriguing because it fills gaps left by stellar processes. Stars cannot produce black holes below about 2 stellar masses, but primordial formation has no such limit. If tiny black holes exist, they would be primordial. The smallest primordial black holes would have evaporated by now through Hawking radiation. Black holes lighter than about 1 billion tons would not have survived the age of the universe. They would have radiated away all their mass long ago. Any remaining primordial black holes must be above this threshold. Could primordial black holes explain dark matter? This is one of the most exciting possibilities. Dark matter makes up roughly 85% of the matter in the universe, yet we have never directly detected it. We observe its gravitational effects on galaxies and cosmic structure, but its identity remains unknown. If primordial black holes formed in sufficient numbers with masses around the mass of an asteroid or larger, they could account for some or all of dark matter. They would interact gravitationally, exactly as dark matter does, while emitting no light and being impossible to observe directly. Searchers for primordial black holes have used various techniques. Gravitational microlensing looks for the brief brightening of background stars when an invisible mass passes in front. Gravitational wave observations search for the signatures of primordial black hole mergers. Studies of the cosmic microwave background constrain how many primordial black holes could have existed in the early universe. So far, no definitive detection has been made. Various mass ranges have been constrained, but not completely ruled out. The window where primordial black holes might still hide grows narrower with each passing year, but it has not closed. In late 2025, the gravitational wave detectors reported a merger involving black holes with masses potentially below what stellar processes can produce. This raised the possibility that at least one black hole involved was primordial. Analysis continues. If we ever confirm the existence of primordial black holes, the implications would be profound. They would be messengers from the first moments of cosmic history. Their properties would reveal conditions in the early universe that we cannot probe any other way. Their abundance would constrain theories of inflation and the Big Bang itself. Primordial black holes remain unconfirmed, but they are permitted by physics. They are compatible with our understanding of the early universe. And they might be out there right now, invisible ancient wanderers, carrying information from the moment everything began. We have traveled far, from the smallest black holes formed in stellar death to the ultramassive titans anchoring distant galaxies, from the first image of an event horizon to the first sound of 2 black holes colliding, from the slow death predicted by Hawking radiation to the theoretical tunnels that might connect distant corners of space-time. Black holes are not just objects, they are challenges. They test our understanding of gravity, of quantum mechanics, of information itself. Every question we answer about them reveals 10 more we cannot yet address. The universe created these monsters, and now, slowly, we are learning to understand them. The journey continues. New telescopes will capture sharper images. New detectors will hear fainter gravitational waves. New theories will emerge to explain what we find. And perhaps, one day, we will answer the deepest questions these dark objects pose. Until then, they wait, silent, invisible, shaping galaxies, warping time, guarding secrets we have barely begun to imagine. The black holes are patient. We should be too.